In this unit, we will look at certain circuit theorems which are useful for circuit analysis, which are useful for deriving other circuit theorems, and which in some cases make certain types of circuit analysis very convenient. Okay. And some of the theorems are also used for abstracting a large circuit into a simpler circuit. We will see all of these things as we go along. The first theorem that we will take is something that we have already used. It is the superposition theorem. What we said earlier was that if we have independent sources and linear components, then we can find the solution to the circuit by taking the independent sources one by one, that is keeping one of them active and setting the values of all the other ones to 0, and find individual solutions, add them all up to find the solution when all the independent sources are acting together. Okay. Now, based on the general analysis we have done, like nodal analysis or mesh analysis, this can be easily proved. That is what I am going to do now. Okay. Let me take this circuit that we have considered earlier while carrying out nodal analysis. It has two current sources and a voltage source. Now, if you want to see how this is to be analyzed, you can go back to the lesson on doing nodal analysis with independent voltage sources. Okay. So, here I am just going to use the results which we have already derived. Okay. So, now you can see three sources here. The current I 1, the voltage source V 0 and the current source I 2. Okay. Now, if we carry out nodal analysis of this, we will arrive at these equations. Okay. This is the G matrix times the unknown vector of node voltages being equal to the vector of independent sources. Okay. As I mentioned earlier while carrying out nodal analysis, this source vector, although I use the letter I to denote it, in this case it contains both currents and voltages. Okay. Now, I have taken this circuit as an example. In all cases, the setup of equations, will be of this form, G times the unknown vector being equal to the source vector. Okay. So, clearly we can solve for the node voltages, the unknown vector V, by inverting G. Okay. So, let me write this down for this particular case, taking this source vector. Okay. So, the solution, that is the unknown node voltages, can be obtained by this expression, and I will write out the source vector explicitly like this. Okay. Now, clearly this vector over here can be written as I 1 0 0 plus 0 V 0 0 plus 0 0 I 2. Okay. So, now this whole thing equals G inverse times this entire thing, the summation on the right hand side. Okay. So, essentially we have to form this summation and multiply the whole thing by G inverse on the left side. Okay. That will be equal to G inverse times the source vector. Now, I will expand out each of these terms to get Okay. What it says is that the complete solution to the node voltages V is the sum of this and that one. Now, if you look at each of these terms, let us take this one for instance. What is it? It is J inverse times I 1 0 0. Basically, this is this whole thing here is the solution when only I 1 is non-zero and V 0 and I 2 are both 0. In other words, this is the solution when only the current source I 1 is acting and the other sources are deactivated. Okay. Similarly, this one is the solution when only the voltage source is acting and the others are deactivated. Okay. Because you can take this general solution, the complete solution over here, set I 1 equal to 0 and I 2 equal to 0, you will get this one. And similarly, you get the third one when you set I 1 equals 0 and V 0 equals 0. So, this is the solution when only I 2 is active. Okay. So, in this case only I 2 is active and in this case only V 0 is active. Okay. So, it says that the complete solution when all three sources I 1, V 0 and I 2 are acting together equals the solution when only I 1 is acting and the others are deactivated, the solution when V 0 is acting and the other two are deactivated, and the solution when I 2 is acting and other two are deactivated. Okay. And this is exactly the statement of superposition theorem. Okay. This is the solution with all sources active. This is nothing but the solution with only I 1 active, and this is the solution with only V 0 active, and finally, this is the solution with only I 2 active. Okay. So, this solution with all sources active being the sum of the solution with only I 1 active plus the solution with only V 0 active plus the solution with only I 2 active. This is the superposition theorem. It is basically a result of linearity of equations. In this case, we have expanded out the matrix multiplying the sum of 3 vectors as the matrix multiplying individual vectors and summing them together. Okay. So, the consequence of the equations governing the circuit being linear is superposition. Okay. Now, why is it useful? It is useful because sometimes it simplifies analysis. Instead of analyzing the circuit with all 3 sources acting together, you can analyze it with one source acting at a time and add up the solutions. Okay. Now, I illustrated it with a particular circuit which had 3 sources. Now, that is just for example. Okay. You can easily see, you can have an arbitrary source vector and you can always represent it as summation of a number of source vectors, where in each source vector only one of the sources is non-zero. Okay. And you will get exactly the same result, right. So, if you want, you can just go ahead and complete the proof for some general case and not for the particular circuit I have shown, but the reasoning I have shown applies to all the circuits. Okay. And of course, you can also show the same proof using mesh analysis. It is not the analysis method that is important here, it is the linearity of the resulting equations which govern the circuit. Okay. So, if we have independent sources and linear components in our circuit, we can always represent the equations as a set of terms which are linear in the variables being equal to some terms which are a combination of the independent sources. Okay. And because these equations are linear, you have this property of superposition. We have seen that the node voltage vector in presence of 3 independent sources can be written as the solution with only I1 active and the other two set to 0, only V0 active and the other two set to 0, plus only I2 active and the other two set to 0. This is the superposition theorem. Okay. As I mentioned, we do not need this particular circuit or only 3 sources. We can have any number of sources and you can superpose the results from them when you are looking at node voltages and consequently any voltage or current in the circuit. Okay. All voltages and currents in the circuit can be obtained from superposition. Okay. So, this is the node voltage vector. By implication, we can also superpose all voltages and currents. Okay. So, that is the proof, one of the possible proofs, because you can prove that superposition holds good for a set of linear equations in many ways. Okay. Now, another point I want to highlight here is that if you look at these individual solutions, this will consist of a vector of 3 numbers, vector of length 3. Let me just take a general form of J inverse and I will call the entries R11, R12, R13, R21, R22, R23, R31, R32, R33. Okay. So, now if you compute J inverse times I1 0 0, it will pick out the numbers from the first column of this. Okay. We will have, this will be R11 I1, R21 I1, R31 I1. Okay. So, this will be the vector. This is the response due to I1 acting alone. The important point I want to mention here is that this is simply proportional to I1. Okay. So, if you have a single independent source in the circuit, then the solution everywhere in the circuit, whether it is voltage or current, will be proportional to that independent source. Okay. You can see that this is now a vector of 3 voltages V1, V2, V3. So, V1 is proportional to I1, V2 is proportional to I1 and V3 is proportional to I1 when I1 is acting by itself. Okay. So, as I said, with a single independent source, this is always the case that every response in the circuit, whether it is voltage or current, is proportional to the excitation. And similarly, when V0 is acting by itself, we will have the solutions being proportional to V0. And finally, when I2 is acting by itself, all solutions will be proportional to I2. Okay. So, this is proportional to V0 and this is proportional to I2. So, to summarize, if you have a single independent source in a linear circuit, what this means is that all components other than the independent source are linear. these are linear. So, that means that they can consist of R's, resistors and controlled sources. Okay. Capacitors and inductors are also linear, but their solution comes out slightly differently. So, we will not deal with them now. Okay. So, with a single independent source in a linear circuit, all responses, and by responses I mean voltages and currents. Okay. So, these are the responses that we consider are proportional to the value of the source. And if you have multiple sources, all responses, that is whether they be voltages or currents, are a linear combination of the sources. If you take a particular variable node voltage V 1, it will be R 11 I 1 plus R 12 V 0 plus R 13 I 2. The point is that it is a linear combination of I 1, V 0 and I 2. The proportionality constants will be different for different quantities. If we take some other quantity, let us say the second node voltage V 2, it will be R 21 I 1 plus R 22 V 0 plus R 23 I 2. Okay. So, it is also a linear combination of I 1, V 0 and I 2. Okay. So, this is something again you have to keep in mind, that if you have multiple sources, every quantity in the circuit, and by quantities I mean voltages and currents, not power specifically, each one will be a linear combination of all the independent source values. Okay. So, you can use that fact also to find the solution in certain circuits in certain situations.